Hello and welcome to this module 14. In this module, we will be seeing about a commonly used a microcontroller called the AVR. So in this module, students will understand the components of a microcontroller, instruction formats of a AVR microcontroller, and the flow of instructions in the AVR microcontroller. So we've already seen about a microprocessor system already. So a microprocessor system, also called as a micro-coded processor, is an IC that contains the digital logic to implement a computer, except that it doesn't have any external memory or input-output devices. So we interface the microprocessor or the micro-coded processor to memory and input-output devices to make a microcomputer. So generally these microcomputers are used in a standalone mode and are used to generally control different systems, and thereby they get the name microcontrollers. So some of the common support circuits that are used along with the microprocessor to create a microcontroller includes clocks and reset circuits, buffers, latches, address decoders, interrupt controllers, timers and counters, cache memories, input-output interfaces, and different types of buses. So here, now we're going to see the AVR microcontroller in a little bit of detail. So AVR stands for Advanced Virtual RISC Microcontroller. RISC stands for Reduced Instruction Set Computers, which means that they generally have a fewer number of instructions, and also these instructions are simple and small. So here is the internal architecture for the AVR. So as you can see, we have our AVR CPU, which basically contains the ALU inside it, and a set of register files, etc. So then it also shows that we have three external memories. One is your EEPROM. The second one is your flash memory, or called the program memory, or also called the RAM, and the third one is your SRAM. So generally we have instructions are stored in your flash memory. The SRAM memory is generally referred to as your data memory, and to store memories for a longer time, we also make use of the EEPROM, which is electrically erasable, programmable, read-only memory. So as we see, the rest of it is support circuitry. So we have our clock and watchdog circuits, power management circuits, programming circuits over there. Then we have a bunch of timers, and then we have analog to digital converters, serial interfaces, communication interfaces, and input-output ports, which are also called as general purpose input-output ports, or pins. So looking into the AVR's CPU, it is a 8-bit processor, hence it uses a 8-bit microprocessor in there, and it has an 8-bit ALU. So your inputs and output to the system, the ALU, is all of 8 bits. So we also have a register file. As you can see, a register file is of size 32, and they are actually can be referenced by simply using R0 to R31. So we also have the program counter, which is nothing but a pointer that points to the instruction that it's going to execute. And we have our instruction decoder, the instruction decoder takes in the instruction from your program memory, and those instructions are split into two, namely the opcode and the operands. Then the opcode is actually sent to the ALU, and the operands are used along with the decoder to either access this register file or access data in your SRAM or access data in your program memory or ROM. So it is very important to note that every instruction is divided into opcode and operand or operands. So here is a simple example. So here you can see this is a pseudo representation of an instruction. So we are actually simply trying to move a value that is in memory location 17 into a register A. So therefore this opcode would correspond to a move operation, and then this operand is going to correspond to memory location 17, which will nothing be R17. So we're going to take the value from R17 and move it to memory location referred as A. So in general, we would write the assembly code, use an assembler to generate the machine code, which is nothing but a value of zeros and ones. But in general, these machine codes are not represented as zeros and ones. They are actually represented as a hexadecimal value, and hence we get the word or the term hex file. And the hex file is the one that is actually programmed into your flash memory, that process is what we call as flashing or programming the microcontroller. So here is a list of all instructions supported by the AVR 8-bit family. So you can see that there is a fewer number of instructions, and these instructions are smaller in size, which means they only have either one or two operands, and the instructions are very basic in functionality. So the AVR instruction format based on the operands are shown here. So here you can see that an instruction to access the register file is shown here. So say for example we want to do an operation which is adding. So we go to our source destination, take the value which is here, and then we want to take the value from your destination address, which is here, add them up and put them back in your destination address itself. So as you can see here, the control word size of your AVR is 16 bits. But if you are actually trying to access the RAM location, then you can see that your instructions are collectively 32 bits. Your first block, which has the operand and then the destination register, and here you have your data address corresponding to your RAM location. Similarly, over in the next part, as you can see, whenever we want to access data from the program memory, so the program memory can be also used to store data. So if I'm actually trying to access data from the program memory, so here you can see that is the operation followed by 22 bits of address for looking into the program memory. So typically, since you only have a size of 0 to 31, which is 32 bits, so this length of this is going to be 5 bits. But here you could have sizes anywhere from 1K to multiple few hundred kilobits. So therefore you would need a larger address for it. Therefore that's why it's occupying 32 bits. And similarly, in terms of the program memory, we could go to a few megabits. So therefore you need a much larger address to access that memory location. So now we're going to see some simple examples. So in the first instruction that we are going to see is called LDI. LDI stands for load immediate. So what it's saying is if I want to move a constant, so here K is the value of the constant, into one of these register files location, so we can use the LDI. So here is an example which says 53 is moved or loaded into R16. So the R16 value here after executing that instruction is going to be 53. Similarly, here you can see LDI R19, 132, a decimal value of 132 is moved in there. You can also do a hexadecimal representation, and hexadecimal value of 27 is moved into R23. So the next type of instruction we're going to see is called the arithmetic and logic instructions. So we have instructions to perform add, subtract, multiply, and then also a bunch of logic operations like AND, OR, XOR, and so on. So here again you can see here is our template for our add. So we have RS, which is your source destination, D is your destination. So we take the value from RS, could be any one of these locations in these register file, add it to the destination register, again could be any one of them in this, and then we add them and then we place them in the destination. So here is an example. We take the value from R9 and add it to R25 and put it back in R25. So here you can see always the operation goes from the right towards the left. So similarly here, take the value in R30, add it with R17 and put it in R17. So an example, for example, if you want to calculate the value of say 19 plus 95, so in order to perform this, these are two constants. So first we need to load these values into a particular register in your register file, and then you add and update your destination. So here we are going to use R16 to hold the value 19, R20 to hold the value 95. Now you can see R20 is added with R16 and then it's actually placed back on R16. So at the end of this computation, R16 would have a value which is 95 plus 19, and R20 will still remain at 95. So the AVR generally pertains to what we call as a load store architecture. So that actually comes from a typical processor which goes through 4 stages when it executes an instruction. So whenever we want to execute an instruction, we first need to fetch or load the instruction from the program memory. Then we would need to decode it. Then we will need to execute that instruction or the operation and then store the resultant back into the register. So therefore we have these 4 stages, but in the case of a AVR, as you can see, we have a 2-stage instruction pipelining. So when we have like an instruction LDS, which is going to load from this memory location. So as you can see, this one will be a memory location in your RAM. So that's why you have, instead of LDI is for immediate, we have LDS, which is load from storage, so which is your RAM. So we are going to load from this memory location into R20 and then take the value from R21, add it to R20 and update R20. So we have these 2 instructions. As you can see, the first instruction is loaded and it's going to be decoded, and then when it actually goes to the execute at the store stage, the next instruction is now loaded and decoded. So this is why it is called as this two-stage instruction pipelining, where at a given time you have two instructions in your architecture. And also another point to note is that the AVR processor has two different memories connected to on a separate bus. So here you can see there is a separate bus for your code memory, which is also your program memory, which is also your instruction memory, and then there is a separate bus for your data memory, which stores the data. For example, this would be your SRAM. So since it has two separate buses to access both these memories individually, so that is called as a Harvard architectures. So generally a RISC processor pertains to a Harvard architecture. So in the case of the CISC, which is the complex instruction set computers, where you have more number of instructions and you have more complex instructions, so there is only one bus that connects both code or the program memory and the data memory. So another point to also note is, as you can see, that every bus, whenever it is connected to the memory, it is of three sets. One, which is the data bus, which handles the data to and from. Then there is this address bus, which supplies address to the memory location. And then the control buttons are nothing but the control signals to read and write data from a memory. So in terms of the AVR's data space or data address space, so here we can see we have our CPU. This is your program memory or your flash memory. So this is your RAM and this is your EEPROM. And the rest of it is, all these are nothing but your peripherals or special circuits that are there. So the program memory is where the instructions are stored. They also call the flash memory. So then we have your EEPROM that is used whenever you want to store data for an extended period of time. And then we have your RAM location, and then this is your internal register file. So the internal register file is generally referred to as the general purpose registers, which are from R0 to R31, then followed by your RAM block, which is here, but the portion of the RAM on the top is reserved for some special registers, and they're actually called special function registers. And those special function registers are nothing but registers that manipulate your other peripherals or interface circuits, like for example timers or oscillators, interrupts, ports, and other peripherals. So all the configuration and status registers are basically part of the standard input-output registers. And then that's the top part of your RAM. The bottom part of your RAM is actually used for your general purpose storage of intermediate data in the microcontroller. And as you can see also that the bus itself is of three, made up of three, which is the address bus, data bus, and the control bus. So here is a detailed look of your standard input-output registers. So here you can see you have a set of registers, say for example, to control the ports of the microcontroller. So here you have some of these registers are used to control the timers. You have registers for your EEPROM. You have registers for your ADC. You have registers for your serial communication interfaces, and so on and so forth.